Okay, welcome everybody. Today we are going to talk about lesson number 28, and this is still section 2.7. We're still talking about nonlinear inequalities, but today we're going to focus on rational functions. Remember, those are the graphs from 2.6 with all the discontinuities and asymptotes. The general procedure is still the same of finding the critical values, setting up your test intervals, and then interpreting them in terms of the inequality. But there are some small but important differences that we have to consider. So let's go ahead and dive right in. So first of all, when it comes to rational functions, we have to extend our definition of critical values. So in the first bullet, please make sure you're aware that for rational functions, the critical values now include any of the zeros, which are of course the x-intercepts, any of the wholes, or also known as the points of discontinuity, and any of the vertical asymptotes. So you basically have way more options for what can be a critical value. Basically what this first bullet says is it's anywhere that the numerator or denominator is equal to 0. So when it comes to rational functions, you're going to have many more critical values. Critical values continue to be the only values of x where the graph can change signs. So just like before, this has to be in relation to 0. If you kind of think about what the graphs of rational functions look like, remember that oftentimes when you had a vertical asymptote, one half of the graph would be going down to negative infinity, the other part of the graph would be going up to positive infinity. So as far as we're concerned, that is considered to be a change in sign. So hopefully it makes sense why those have to be added to our list of critical values. So now that we have extended the definition of what critical values are, let's go ahead and get to it. So here's question number 1. You're trying to solve the rational inequality 3x minus 5 over x minus 3 is less than or equal to 1. So hopefully the first thing you realize is the fact that this is a 1 is really not very good news. Again, we only can ever solve these in relation to 0. So we're going to have to go ahead and get that 1 to the left-hand side. So these are obviously a little bit more intense algebraically, but I think we can handle it. So we're going to go ahead and subtract the 1, which makes this 3x minus 5 over x minus 3 minus 1 is now less than or equal to 0. We're going to go ahead and change that 1 over 1 into a common denominator. So 3x minus 5 over x minus 3 minus, and so we're going to change x minus 1 into x minus 3 over x minus 3. And again, that's just finding, a common denominator. So then from here, we're going to go ahead and actually put them together with a common denominator. So we're going to get 3x minus 5. Make sure you distribute the negative on the top, minus x plus 3 over x minus 3 is less than or equal to 0. And if you combine like terms, you're going to get a 2x. You're going to get a minus 2 over x minus 3 is less than or equal to 0, which is going to give you, factor out the 2. So what we have done so far is we have basically rewritten the problem into one that we can solve more easily. So again, just to reiterate, you have to be in relation to 0. When it comes to rational functions, you're often going to have to find a common denominator. Make sure you distribute any negatives, combine like terms, try to factor as much as you possibly can, which ultimately gives you 2 times x minus 1 over x minus 3 is less than or equal to 0. So once you're clear how we got to there, I'm going to go ahead and move to the next screen. So let me just go ahead and copy that for a second. So 2 times x minus 1 over x minus 3 is less than or equal to 0. So this is now the inequality that we're solving. So in order to do this, we're going to have to go ahead and locate the critical values. As a reminder, if you go back, the critical values are basically anything that make the numerator or denominator equal to 0. So if you look at the numerator, nothing comes from the 2. The x minus 1 yields a 1. The x minus 3 yields a 3. So my critical values in this case, and let me just make sure I call them as such. The critical values are 1 and 3. Something that I want to point out, something that I like to do. So wherever the vertical asymptote is, which is where there is a uncanceled factor of the denominator, I always like to just denote that, because when it comes to inequalities, because this is a less than or equal to, you are not going to be able to include the vertical asymptote ever. So I just like to make a note of where they are so I don't forget and don't make a mistake. So now that I have my critical values 1 and 3, I'm going to go ahead and test. Remember that when you're testing, you are choosing values from each of the intervals. So I'm going to go ahead and start by choosing something bigger than 3. And again, I personally always like to choose 10. I just think it's a very easy number to do so. So looking at 2 times x minus 1 over x minus 3, if I plug a 10 into the numerator, I'm going to get a positive. If I plug a 10 into the denominator, I'm going to get a positive. And of course, a double positive yields a positive. Something between 1 and 3, the value that seems to make the most sense, I would think, would be 2. If you plug a 2 in the numerator, you're going to get a positive. In the denominator is going to give you a negative, and a positive over a negative, of course, yields a negative. Something that is less than 1, again, you could choose anything. I'm going to choose what I think is the best one, which is 0. If you choose a 0, you're going to get a negative in the numerator, and you're going to get a negative in the denominator. And of course, a negative over a negative is going to yield a positive. So even though you had to find the critical values by not only considering the zeros, but also considering any wholes or vertical asymptotes, that was slightly different than the polynomial interpretation, but certainly the sign analysis is similar. So now in terms of finding the answer, you are trying to tell me where the graph is less than or equal to 0, but keep in mind, you can never include a vertical asymptote. So if I want to know where the graph is less than or equal to 0, I'm going to start at 1, and I'm actually going to include 1 because of the fact that it's an equal to. Then I'm going to go all the way to 3, but I'm not going to include 3 because of the fact that it's a vertical asymptote. So my answer to this problem is bracket 1 to 3. And again, it's because less than or equal to 0 means anywhere that there's a negative. You're going to include the x's where possible. So include the 1 because that's a 0, but don't include the 3 because that's where the vertical asymptote lives. So let's go ahead and try another one. So here in number 2, again, notice that they are on opposite sides, which as far as we're concerned, really doesn't help us. So we have to start by subtracting everything to one side, and I personally go left side. So 5 over x minus 6, and I'm going to add in a parentheses, minus 3 over x plus 2, and now we're greater than 0. We have to go ahead and find a common denominator, and the common denominator of x minus 6 and x plus 2 would, of course, be those two things multiplied times each other. In order to turn that into a common denominator, you would have to multiply this expression here times x plus 2 over x plus 2, which is why we're going to wind up with 5 times x plus 2. Then you're going to have to multiply this second quantity here, so negative 3 times x minus 6 over x minus 6. Let's go ahead and distribute in the numerator. So in the numerator, that's going to be 5x plus 10 minus 3x plus 18. Make sure that you distribute this negative. So in the numerator, that is going to give me a 2x plus 28. If I factor the numerator, that's 2 times x plus 14. And then don't forget my denominator, which I just left out for a minute to save myself a step. And this is going to be greater than 0. I'm sorry, this should really be greater than 0. So 2 times x plus 14 over x minus 6 times x plus 2 greater than 0. Again, this is now the rational function in question that I am trying to solve. You have to make sure that you get everything to one side in relation to 0, or it's not going to work. Just like the previous one, let me go ahead and pull up a nice fresh slide here. So let me just go ahead and write that again. So 2 times x plus 14 all over x minus 6 times x plus 2, and that's going to be greater than 0. I have to go ahead and find the critical values. And remember, when it comes to rational functions, the critical values are anything that make the top or bottom 0. So per the top, I'm going to get a critical value of negative 14. Per the bottom, I'm going to get 6 and negative 2. You're going to go ahead and set up your number line using the critical values in order. So negative 14, negative 2, and 6. Obviously, the more critical values there are, the more work this is because the more testing you have to do. But it's mostly just annoying, not necessarily hard. And again, I personally, you don't have to do this, but I always like to just indicate where the vertical asymptotes are. So I remember never to include those. And again, the vertical asymptotes come from non-canceled factors of the denominator. So now it's time to test. I'm going to start by testing something bigger than 6. I'm going to choose 10. So if I choose 10 in the numerator, I'm going to get a positive. Then if I put it into x minus 6 and then x plus 2, looks like I'm going to get positives all around, which is going to give me a positive. Something between negative 2 and 6, when possible, choose a 0. So in the numerator, looks like a positive. In the denominator, 0 minus 6 is a negative, plus 2 is a positive. That's going to be a positive over a negative, which yields a negative. Something between negative 14 and negative 2, I'm going to choose negative 10. So negative 10 in the numerator is going to give me a positive. In the denominator, negative 10 minus 6, negative 10 plus 2. That looks like I'm going to get a positive over a positive, which is ultimately going to make it positive. And then something less than negative 14. Again, I personally just always like to choose the intervals of 10 where possible. I just think it makes it easier. But again, you could choose anything that's a representative sample from that interval. So negative 20 in the numerator, that's going to give me a negative. And then negative 20 minus 6 is another negative. Negative 20 plus 2 is another negative. That's ultimately going to be a negative over a positive, which is going to yield a negative. So now that I've done my sign analysis, I have to make sure that I do my answer. And remember, I want to know strictly where the graph is greater than 0. So whilst you're never going to include the vertical asymptotes anyway, you're actually not going to include any of the critical values because it's strictly greater than 0, which means you want the locations where there's a positive. So that means your first part of the answer is from negative 14 to negative 2. And your second part of the answer is from 6 to infinity. And it is going to be parentheses for everyone, again, because of the fact that there is no equal to. So again, quality over quantity, I think, is the way to go here. Those two problems are really a good representative sample for what you're going to see tonight. But there is a little bit more to consider. We want to consider the graphical connection to this. So take, for example, the graph of the rational function, x squared plus 4x plus 3 over x squared plus 2x minus 3. So we're going to solve this exactly the same way we did the previous two problems in a minute. But before we do that, we want to talk about what do the answers mean in terms of the graph. Because if you had the graph in front of you, you could answer these inequalities without actually doing all this work. But ultimately, the answer should be the same. So if we take a look at how this graph becomes here, if you were to go ahead and factor it, you would factor the numerator as being x plus 3 and x plus 1. If you were to factor the denominator, that would give you x plus 3 and x minus 1. So then notice that because of the fact that you have those x plus 3s, that is where you would get your whole. The x plus 1 in the numerator, that's where you would get your 0. The x minus 1 in the denominator, that is where you would get your vertical asymptote. Your horizontal asymptote would be 1 over 1, which is 1. Your y-intercept would be negative 1. So again, this is why we spent so much time in section 2.6, just kind of making sure that you understand how the graph comes about. That never quite goes away. So if I was going to ask you to solve each of these 5 either equations or inequalities, and I already had the graph in front of me, I could do that without a sign analysis, but then we're going to do it in a minute just to see how the two are related. So if I first want to know where is g of x equal to 0, that basically means I want to look at the graph and find all the places where it crosses the x-axis. Hopefully you would agree that the only location where that occurs is here at x equals negative 1. Compare that to number 2, where is g of x strictly greater than 0? So greater than 0, of course, means above the x-axis. So maybe that would be helpful to write. So on the x-axis is what you're solving for in number 1, strictly above the x-axis. So if I look for where the graph is strictly above the x-axis, it's here and here. But again, strictly above means you're not going to have any brackets. You're only going to have parentheses. And you also have to be sure not to include this whole. So from what values of x is it above the x-axis? Well, starting at negative infinity, taking a break at the whole, then from the whole to the x-intercept, which is negative 1, and then from the right of the vertical asymptote, which would be 1 to infinity. So it's basically all the places where I kind of shaded it in purple, but notice I had to take a break at the whole, I had to take a break at the vertical asymptote, and I'm using parentheses all over because of the fact that it's strictly greater than, which means above the x-axis only. For number 3, if it's less than 0, that strictly means that I'm trying to solve where it's just below the x-axis. So below the x-axis only, and it turns out that the only place where that occurs would be right here. Again, because of the fact that you're below the x-axis only, you're not going to include any of the values, so parentheses for everybody, and it looks like that would be from negative 1 to 1. Hopefully it should make sense that if you were to add up all the places where the graph is on, above, or below the x-axis, that would include all the real numbers. That should just kind of, be intuitive. But so now the last two. So greater than or equal to 0, make sure you know that that means on or above the x-axis. Where in number 5, that means on or below the x-axis. So if we go back to on or above the x-axis, we're going to get the same answer as we did in number 2, except for the fact that we're now going to do it with brackets where possible. So it's still going to be from negative infinity to negative 3, and from negative 3 to negative 1, but we are now going to be able to include that 1 because of the fact that it's a 0. So again, where is it above the x-axis? That's here. Break at the whole, from the whole to the 0, and you can now include that 0 with a bracket. Then it's everything here to the right of the vertical asymptote, and you're never going to include the vertical asymptote, which is why it's parentheses 1 to infinity. So again, compare number 2 to number 4. You can see that it is in fact the same solution set, except now that you have a bracket. And similarly for number 5, if you compare 3 and 5, where is it on or below the x-axis? It's still going to be this right here. The only difference being that you can include the 0, which is negative 1, but you can never include the vertical asymptote. So just to be clear, this is an alternative way to solve a rational inequality if you have the graph in front of you. Same thing for polynomials. If you have the graph in front of you, you can just look at it and tell me where is it on, above, or below the x-axis. We've kind of already done that throughout the year, but I do want to make sure that you can see the connections. So just to kind of solidify things, here is the same exact problem. We're going to go ahead and solve where is it less than or equal to 0, but we're going to do so with a sign analysis. Here's the thing. If you didn't already have this graph in front of you, making one would take more time than is required to go ahead and just do the sign analysis, but I do want to make sure you understand that they're the same. So I would start by factoring x plus 1, x plus 3, x minus 1, and x plus 3 less than or equal to 0. Even though you have a common factor, you are not going to get rid of it. So critical values, this is the first time today that we've seen where there's a common factor, but remember our critical values are anything that makes the top or bottom 0. So per the numerator, I'm going to get critical values of negative 1 and negative 3. Per the denominator, I'm going to get 1 and then negative 3 again. So if I go ahead and set up my number line in order, negative 3, negative 1, and 1, And again, I just like to indicate that this is a vertical asymptote. And then at -3, make sure you're aware that this is where the hole is. Those values are never going to be able to be included. So I want to kind of keep that in mind. And remember, ultimately, we're solving less than or equal to 0. Excuse me. So it's time to go ahead and start testing something that's bigger than 1. Again, I personally like to choose 10, and I'm going to be testing here in my factored form. So if I test 10, I'm going to get a positive times a positive, and then positive in the denominator. You're going to go ahead and get a positive. Then between -1 and 1, I choose my old friend 0. That's going to give me positive over negative positive. That's ultimately going to be a positive over a negative, which is, of course, a negative. Something between -3 and -1, -2 is probably the best one to choose. So be a little more careful as you get closer to those actual critical values. So -2 plus 1, that's a negative. Plus 3 is a positive. -1 is a negative. Plus 3 is a positive. That's a negative over a negative, which is a positive. Something less than -3, I'm going to choose my old friend -10. So in the numerator, that's going to be a negative and a negative over a negative and a negative. That's going to be a positive over a positive, which is, of course, a positive. So then, in order to solve this problem, again, the answer, you are trying to tell me where the graph is less than or equal to 0. So you're going to locate all the regions where it's negative. Less than or equal to 0 means you could include the critical values where possible. You can include the -1 because it's a 0. You can't include the 1 because it's a vertical asymptote, which means your answer would be -1 to 1 with a bracket on the -1 and a parenthesis on the 1. Just to clarify, so less than or equal to 0, if we go back a slide, this is the answer to number 5. And notice it is, in fact, the exact same. So if you had the graph of a rational function in front of you, it would make sense to use it. If you don't, I strongly recommend you go with the sign analysis. So what I'm going to ask you to do here for our final problem of the day is I'm actually going to ask you to try it. So I'm going to pause it. Not only is it a good question, but it's also a multiple choice question, which some of us, based on what I've been seeing so far from the 2.6, continue to need practice with. So I'm going to go ahead and pause it while everybody tries it and tries to choose the correct answer. And then when we come back, I will go over the answers. Okay, so assuming that you have tried it, we're going to go ahead and rewrite this. So 3 over x minus 3. And sorry, just to be clear, the answer is E. So if you were trying it and got an answer of E, congratulations, you're correct. If not, let's go through it. So 3 over x minus 3 minus 2 over, and I'm going to factor x plus 3, x minus 3, and this is all greater than 0. Remember, you have to be in relation to 0. I'm going to go ahead and find a common denominator. So x plus 3, x minus 3. I would have to multiply the first term by 3 times x plus 3 over x plus 3, and then minus 2. So in the numerator, that's going to be 3x plus 9 minus 2. If I clean that up, that's going to be 3x plus 7 over x plus 3, x minus 3. And that's going to be greater than 0. So this is ultimately the equation, the inequality that you should be solving. Going to go ahead and need an extra slide for that. So again, let me just write that again. 3x plus 7 over x plus 3, x minus 3, and that would be greater than 0. Remember that the critical values come from the numerator and denominator. So -7/3, -3, and 3. I'm going to go ahead and set up my number line. Be sure to put them in order. So -3, -7/3. Make sure you know that this is -2 and 1/3 so that you choose values appropriately. So this is 3. Hopefully at this point you're getting better at the sign analysis. If you go ahead and test values, you should get a positive. you should get a negative, you should get a positive, and you should get a negative. Again, I like to just indicate where the vertical asymptotes are, so I remember to never include them. Because of the fact that you are trying to find where the graph is strictly greater than 0, that means you are choosing the positive locations. And because it's strictly greater than 0, you are not including any of the critical values. So that means you're going parentheses from -3 to -7/3, and then parentheses from 3 to infinity. No brackets anywhere, so parentheses for all, which is why if you go back to the previous slide, just to confirm here, that should in fact be choice E. So just to make sure that that all kind of jives. So just like before, I focused on quality over quantity here in homework 28, 4 problems, all of which you should do with a sign analysis. So tomorrow, we're going to kind of mix and match polynomials and rational functions together and see some applications. So thanks very much for tuning in, guys, and we will catch you next time.